01 knapsack problem. 01 knapsack problem is a classic optimization problem in computer science. This is a variation of the fractional knapsack problem that we had seen when we were learning about greedy algorithms. What did we do in fractional knapsack? We were provided with n different items and a knapsack. What was the task? We had to insert a set of items from these n items that are provided such that the value of this knapsack is maximized. How can you maximize the value? Each item among these n items will be having a weight wi and value vi associated with it. What is this weight? This is the total weight of ith item, and if you sell this complete item, vi is the value that you will get. You can see this as the profit that you will gain if you sell the ith item. So for each item, you know what is the weight of that item and what is the profit you will gain if you sell this particular item. What do you want to do now? You want to insert a set of items from these n items into the knapsack. Why only a set of items? The reason is this knapsack has a capacity W. So the total weight of items that can be held by this knapsack is W, which means you should insert not all the items, because if you insert all the n items, weight will be more than W. Because of this, you have to select some items out of these n items which are more profitable. You should use those items in the knapsack so that your profit is maximized. Next thing is, why are you putting all these into the knapsack? The reason is, you are a seller. What are you going to do? In the morning, you are going to start from somewhere in the city with this knapsack and you'll roam around the city trying to sell all the items in the knapsack. By evening, you'll conclude your day and you'll have your knapsack empty. That is, all the items in your knapsack will be sold. So what should you do in the morning? In the morning, you already know that a total of W weight is only possible to be inserted into the knapsack. So you should wisely choose those items which will increase your profit, that is, maximize your profit. So this is the problem statement. What is the difference between fractional knapsack and 01 knapsack? In case of fractional knapsack, you were allowed to take a fraction of an item if it cannot be inserted fully. That is, let us say you already inserted some 3-4 items into the knapsack. There is some more space left in the knapsack. Let us say a total of 5 kilograms is possible to be inserted into the knapsack, but the item that is remaining, that is having a total weight of 7 kilograms. This means you can't actually insert this complete item. I'm saying this is the item which is profitable comparatively among the remaining items, but the total capacity remaining is only 5. In this case, in case of fractional knapsack, you were allowed to take a fraction of this item. That is, even though the total weight of this item is 7, you can take a fraction of this item such that this fraction weighs 5. In this way, you were allowed to always go for the greedy method. What is the greedy method? At every step, you will try to choose that item which is having the maximum profit by weight ratio. What is profit by weight ratio? If you do VI by WI, this is what you call as profit by weight. That is, per unit weight, what is the profit you can get for this item? Whichever item is having maximum profit by weight, that is the item which will give you maximum profit if you sell it. Because of this, in case of fractional knapsack, you were allowed to greedily choose the maximum profit by weight item in every step, because whenever you fall into a scenario where the next item is having more weight than the remaining capacity, you were allowed to take a fraction. So this was the leniency that you got. In case of 01 knapsack, this is not allowed. That is, whenever you face a situation where the weight of item is more than the remaining capacity of knapsack, you will have to avoid this item and go for some other item. Because you are not allowed to take fractions. It is 0, 1. What is 0, 1? 0 means you are not taking it. 1 means you are taking it. Either take the full item or don't take it all. You are not allowed to take fractions. This is 0, 1 knapsack. Let us see what is the problem here. If you choose greedy algorithm, why is it that you will not always succeed? I'll show you a simple example. From this, it will be clear for you why you should not choose greedy algorithm while solving 0, 1 knapsack. Let us say you have only 2 items. Okay. Weight, let us say there is weight Wi and value Vi. Okay. Weight Wi and value Vi associated with each item. You have only 2 items, first item and second item. Let us say first item is having a weight of 1 and value of 2. Second item, let us say, has a weight of 10 and value of 5. We have a knapsack and this knapsack is having a total capacity of 10. What is the profit by weight ratio here? If you take Vi by Wi, what will you get for the first item? It will be 2 by 1, which is 2. For the second item, it will be 5 by 10, which is 0.5. Clearly, if you go for the greedy algorithm, you are going to pick the first item and then only you will go for the second item. Why? Because profit by weight ratio is higher for the first item. What will happen if you make this greedy choice? If you make this greedy choice, you will first pick the first item, which means you are now getting a total profit of 2. 2 is your total profit and 1 is the weight of this item, which means the knapsack now has remaining capacity as 9. It totally had 10, from which 1 is used up by the first item, which means you have remaining capacity of 9. What is the problem now? The problem is second item is having a weight of 10, which is more than the remaining capacity. In case of fractional knapsack, you were allowed to take 9 by 10 fraction of the actual item. This was allowed in case of fractional knapsack, which means you were allowed to do this greedy. But in 0, 1 knapsack, because your capacity is 9, remaining capacity is 9, you are not allowed to pick this item which is having a total weight of 10. So your knapsack will only have 1 item and the value of that 1 item will be 2. So what is the total profit you'll get at the end of the day? If you complete this knapsack, which is having only 1 item, which is having weight 1 and value 2, the total profit you will get at the end of the day will be 2. But instead of greedy algorithm, if you had applied a bit more logic, what would you have done? Instead of this item, you would have chosen the second item, which is having weight of 10 and value of 5. Even though the profit by weight ratio is lesser here, you can insert the complete item which is having weight of 10 if you are not picking the first one. If you are not picking the first one, you can pick complete second item, which means at the end of the day, your total profit will be 5. Which is larger, 5 or 2? 5 is larger. That is, if you don't use greedy, then in 0, 1 knapsack, you have benefit. Greedy algorithm is not suitable for 0, 1 knapsack. I showed this example just to show you that you cannot go for the greedy algorithm in case of 0, 1 knapsack. It may backfire. If you can't go for greedy, then what is the option remaining? This is the question. Let us see what are the options that we have in order to solve greedy algorithm. In order to solve 0, 1 knapsack problem. Let us see with a recursive approach first, and then we'll try to optimize this using dynamic programming. So dynamic programming is the final approach we are going to take. In order to understand the path correctly, we'll first see the recursive approach. We'll see where it is going wrong and how can we patch it up using dynamic programming. This is what we are going to learn in this lecture. First of all, we have this 0, 1 knapsack problem and a total capacity of W. W is the total capacity of knapsack. You have n items in total. Each item has a weight Wi and value Vi. This is the scenario. Let us try to write a recurrence relation This recurrence relation should tell us how to choose the items. That is, at any point, how can you decide whether to choose an item or not to choose an item. So we are going to write a simple recursive solution now. Later, we'll optimize this. So let us say this is a recursive solution, knapsack. In 0 and knapsack, you have a total of n items and total capacity W. How can you pick one item out of this and write a recursive relation for the remaining n minus 1 items? This is what we want to know. That is how recursion works. That is, you will start from the top, you will pick one item and then write a recursive relation for the remaining items. This is how you want to do this. So what all are the cases possible? First case is, what if your n is 0? If n is 0 means there are no items at all, which means you can't include anything in the knapsack and your profit will be 0. This is one case. What if W is 0? If W is 0, your knapsack has 0 capacity. In that case also, you cannot include anything and your total profit will be 0. So both when n equal to 0 or W equal to 0, your total profit at the end of the day will be 0. So one case is 0 if either n is equal to 0 or if W equal to 0. If either of these is 0, you can directly say your final answer is 0. So your 0-1 knapsack problem is directly solved if either n or W is 0. If it is not 0, if both of those are not 0, then let us see what are the cases. You have n items. What if the weight of this nth items, at nth item, let us say Wn, if this is greater than W, then what happens? If nth item is having a weight larger than the capacity of knapsack itself, then surely it's not possible to insert this item. So in this case, you have to insert other n minus 1 items and make some profit, which means your total profit is purely dependent on the remaining n minus 1 items and not on the nth item. What is the reason? The reason is that the weight of nth item is more than the total capacity of your knapsack. So in this case, what is your recursive relation? If Wn is greater than W, then your recursive relation will be knapsack of n minus 1 items with a weight W. That is, if your capacity is W and you had the remaining n minus 1 items, this nth item is as good as not having, because the weight of this item is more than the total capacity of knapsack. So this is the case if what happens? If Wn is greater than the capacity W of knapsack. This is the second case. There is one more case remaining. So that is the complex case. That is why I kept it for the end. The remaining cases, if your Wn is less than or equal to W. In this case, whenever the weight of this nth item is less than or equal to the total capacity of knapsack, then you have an option to include this in the knapsack. Let us see how you can include this. So when you have an option to include, you need not necessarily include. That is, you have two options. One is you can include. Second option is you can not include. Let us see what are both these cases, and whatever be the cases, you have to take maximum out of those, because your aim is to make maximum profit. So you have to choose maximum of two cases. First case is you include it. Second case is you don't include it. We already know how to write if you don't include, because that we already learned. So let us write that first. Maximum of first case is knapsack of n minus 1 W. This is the first case, that is not included. We already are done with this case, not included. In case you are not including, you can include remaining n minus 1 items and use the complete W capacity of knapsack. And what is the second case to be filled here? Second case to be filled here is if you are including this item. If you are including this item, then still you have n minus 1 items remaining. But the difference here is your total value will also include the value of the included item. So let us say value of included item is Vn. then your value will be Vn plus what is the value from the remaining n minus 1 items? Knapsack of n minus 1. If I write n minus 1 W, is this right? No, it is not right. Why is this not right? Because you already used up some of the space for the nth item. You are including the nth item and adding the value of nth item. For this nth item, you have used some of the space. So the whole W is not remaining. Instead, W minus Wn will be remaining. So you have to write W minus Wn. This is the only remaining capacity. What is the case? This is the case if your Wn is less than or equal to total capacity of knapsack. So this is your recurrence relation. This is how your recurrence relation looks. First case is whenever your n is equal to 0 or your W is equal to 0. That is either there are 0 items or if total capacity of knapsack is 0. In both cases, your total profit is 0. You can directly say that because you can't include anything now. In case that is not the case, your n and W are both positive numbers, then you have two more cases. First case is if the weight of the nth item is more than the total capacity of knapsack. In that case, your total profit will be whatever profit you make from the remaining n minus 1 items by using complete W capacity of the knapsack. What is the final case? Final case is if Wn is less than or equal to W. That means this item is having a weight which is lesser than the total capacity of knapsack. You have an option to add this item. You need not necessarily add this item, but you have an option to add this item. So if you add this, then what happens? You have to choose maximum of both the cases. If you don't add, then it will be knapsack of n minus 1 W. That is, you can use complete W weight for the remaining items and find out the profit. Otherwise, if you are adding this item, then your profit will be whatever is the value provided by this item plus whatever is the value you can obtain from the remaining n minus 1 items, but with a total capacity of W minus Wn. Why is this W minus Wn? Because Wn is already used up by the present item. So this is the recurrence relation. If you use this recurrence relation, 100% you are going to get right answer. That is for sure. If you use this recurrence relation, you write a recursive solution, you will get the answer. But what is the problem? The problem is that in this case, each item, let us say you have n items, 1, 2, 3, 4, these are your items. Each of those items have two choices here. Either you can include it or you cannot include it. So first item has two choices, second item has two choices, third item has two choices, and so on. And what happens with your recurrence relation? Your recursive solution is recursively going to go through all those choices and finally find you the answer. What is the problem with this? 2 into 2 into 2 into 2 n times, which means total number of ways is 2 power n. There are 2 power n choices, out of which you have to find which is the best choice. If you actually write the complete recurrence relation, that is this recursive solution, and you implement it, the problem is that it is going to go through all the 2 power n choices and your time complexity will be order of 2 power n. So order of 2 power n will be the time complexity of your recursive solution. This is generally the problem is whenever n is larger, your time is going to increase exponentially, and this is not feasible in practical scenarios. So in order to tackle this, you have to find some other way of solving this. If you directly use this recurrence relation, it is going to be order of 2 power n. Let us see, using dynamic programming, how can we bring this time complexity down? We'll see till what point is it possible to bring down and how can we bring this down using dynamic programming. So what is dynamic programming? The only thing we are going to add in dynamic programming is we are going to use the same recurrence relation, the same situation, but we are going to store intermediate results. The problem here is You are solving the same subproblem again and again when you are solving different recurrence relations. Instead, if you store those intermediate results in a table, whenever you want this result again, let us say while solving some other subproblem, you can directly fetch it from this table and you can save the remaining recursive calls in that particular subproblem. This way, we'll be able to bring down the time complexity from this order of 2 power n. So keep in mind, we are going to use same recurrence relation in dynamic programming. The only difference is we are going to store some values. So let us see how we are going to store the values, how we are going to do this. So let us see this here. Keep in mind the recurrence relation. We are going to use the same recurrence relation in dynamic programming. So how we are going to do this is, we'll use tabulation method. In the last lecture, we learned about tabulation. Let us make use of tabulation here. The first thing you have to understand is tabulation is a bottom-up method. That is, we'll have a table. We'll start from the simplest subproblem first, and we'll build the final solution in a bottom-up manner. This is tabulation. So in tabulation, let us see what are the steps to be followed. First thing is, you have to create a two-dimensional table. What is this two-dimensional table for? Table means it is a matrix. We'll call this as DP, the two-dimensional table. This table will be of size n plus 1 cross w plus 1. What are n and w? N is the total number of items that you have, and w is the total capacity of the knapsack, total weight the knapsack can hold. So the first step is to have the table. I told you we are going to use this table to store all the values. So your two-dimensional table will be having size n plus 1 cross w plus 1. Then what are you going to do? Let us understand what this table represents. Let us say one particular element of this table, dp of ij. What is the meaning of this element? Any particular element, dp of ij, this will represent the maximum value that can be obtained by using first I items that are provided if the capacity of knapsack is j. This is what dp ijth element means. What does it mean? It means whatever is the entry you are going to enter in dp ij, that will be the maximum value that can be obtained if you use the first I items and the capacity of your knapsack is j. This is what it means. So you already understood that the final answer will be present in dp of n w, because this will tell you if you use all the n items and the capacity of knapsack is w, what is the maximum value possible. And this is why we are calling it as bottom up. We are going to solve the smallest entry first, and then we'll slowly build the table up so that the entry in dp nw is filled. This is what we are going to do. So what is dp ij? Keep this in mind. This is very important. It is the maximum value that can be obtained using first I items. Here, when I say first I items, keep in mind, I am not saying that you will include all the first I items. I am telling you that first I items are available for selection. You may or may not include it in the bag, but you have first I items available for selection. This is the point. And the capacity at that point, whatever is the total capacity allowed in the knapsack, that will be j. That is what dp ij means. So the next thing, you understood what is dp ij. Next thing is, what is the base case? Whenever you have a recurrence relation, it should have a base case in which it can hit and stop. Otherwise, it will keep making recursive calls again and again. So what is the base case in this scenario? Base case is base case. The base case is if no items are there or the capacity equal to 0. What did we learn? If n is equal to 0, that is no items are there, or if capacity equal to 0, or if w equal to 0. In both these cases, what will you say? You can directly say that the total knapsack value is 0. That is, dp ij, this will be 0. This is what we learned. Why is this 0? Because either if there are no items, then it will be 0, or if the capacity of knapsack is 0, then also you can't add anything. So dp of ij is 0. This is the first thing. Next thing, so this means if you have the matrix, the first row and first column, both of them will be having value 0. Why is it? Because dp of ij, where I is 0 or j is 0, I corresponds to the number of items and w corresponds to the j corresponds to the capacity of knapsack. So both these cases, your total knapsack value will be 0. So your first row and first column are both going to stay as 0. This is the first point. So you got the base case. Keep in mind, we are building this matrix. So while building the matrix, initially we know this is what the first row is. We also know what is the first column. We are slowly trying to build each of these so that we can finally find out the value in this entry. Okay, this is dpnw. This will tell us what is the final capacity, the final value, the total value of the knapsack. So let us go to the formula. See the previous formula, keep this in mind. We are going to use the same formula. The only difference is we are going to store values. Okay, so we are going to use the same formula using the transition formula. The transition formula. What is a transition formula? First case is if your weight, let us say wi, is greater than j. What is j? At whichever point we are, whichever entry in the matrix we are, at that point we are saying, we are considering that the total capacity of your knapsack is j. So whenever weight of the ith item wi, if wi is greater than j, what did we learn? We learned here that if wi is greater than j, that is wn greater than w, same case. In that case, you can't include the item, which means you have to consider remaining n-1 items and the profit obtained using those with a weight of w. This is what we are going to replicate here. How do you replicate the same thing in the matrix? To replicate the same thing, you will say, in this case, my entry dpij, what will this entry be? This will be equal to dp, that is the entry in the matrix, with ith item will not be included, which means the remaining I-1 items may or may not be included, but it will be available for selection. This ith item is anyway useless because it is having weight more than j. So dp of I-1, whatever you got with I-1 items, with a total capacity of j. So this is the way you write it in matrix form. In case your weight of this ith item is greater than j, your dp of ij is equal to dp of I-1 j. That is without having the ith item, with I-1 items, if the total capacity is j, what is the maximum profit possible? So this case is clear. What is the other case? Other case is if your wi is less than or equal to j. So this is comparatively complex case. What is the case here? This is same case as this one, this case. What is this case here? If wn less than or equal to w, you had two things. One is if you are not including this nth item. Other one is if you are including the nth item. Both cases you had to consider. The same thing we are going to do here. One is if you are not including, then knapsack of n-1 w. If you are including, value of this item plus knapsack of remaining n-1 items with a weight of w minus wn. The same thing if you replicate here, what will happen? The same thing if you replicate here, it will look like this. dp of ij, how can you write this? This will be equal to maximum of, what are the two things? One is the same thing. If you are not including, then it will be dp of I-1 j. This is the case if you are not including. But if you are including, then what will be the case? The case will be value of the ith item plus dp of with the remaining I-1 items and what should be the remaining weight? From j, whatever is the weight of ith item that is used up. So the remaining weight is j minus wi, right? The remaining weight should be j minus wi. So this is how you can write recurrence relation for this, recurrence relation in the matrix form. So by doing it in the matrix form, we are storing all the values in the matrix. So if you see here, because you are storing all the values, you can directly take previous values. See, what are you doing here? Instead of solving dpij, you are simply picking the value of dpi minus 1j. What were you previously doing? Previously, you were making a recursive call with n minus 1 items. That means it will keep recursively calling again and again. But in matrix form, you are directly fetching the value. This is where dynamic programming is going to help you. What about the second case? In second case also, if you see, in case of recursive relation, you are making a recursive call when it is not present, and you were making a recursive call here, knapsack recursive call, when it is present. In both cases, when it is not present and present, you were making recursive calls. But once you wrote it in matrix form, in dynamic programming, what are you doing? You are directly fetching the element of the matrix. You are fetching I minus 1 jth element. Here you are fetching I minus 1 j minus wi'th element in the matrix. This is where dynamic programming is helping you. So what will happen? You should fill the complete matrix by using this logic. All the dpij's should be filled in the matrix using this logic. Once your complete matrix is filled, what happens? The last step is whatever is your dp nw. This will hold the final value. dpnw will tell you what is the final value of the final profit you get from the matrix. The next step is, let us actually write this as an implementable code, because that will make it easier for you. That is, let us see how exactly you can write the loop, how you can exactly write this in a programmable way. So let us write that exact thing. So we'll go for the pseudocode. I'll be erasing. So what I'll do is, you understood this thing, right? So I'll erase this and then I'll write the pseudocode. So I'll erase this off. And let us see how the pseudocode will look for the problem. I didn't erase off the actual recurrence relation that is here, because we can refer to it. It will be easier to understand. Let us write the knapsack function. So knapsack, it will look something like this. Knapsack of, what will be the input? Input will be, you have one array w, which will tell you the weight of all items. Then you will have one array which is v, which will have value of all items. And then you will have a value w. W is the total capacity of knapsack. So this w, small w, is an array which is having n different elements inside. That is the weight of n different items. This v is also an array. It has the value of n different items. And this capital W, it is the total capacity of the knapsack. It is a single value. Okay. Let us see how you can write this function. What is the first thing? You want to know how many items are there. So for that, in order to understand n, we'll write n is equal to length of w. Length of w or length of v, whatever you may do, you will get the total number of items. So you got the total number of items here. Then you want a matrix. So dp, this is n plus 1 cross w plus 1 matrix. This matrix is important, and initially you will have all zeros in the matrix. You will initialize this matrix with all zeros. Or if you simply initialize first row and first column with 0, or only the first row with 0, that will also do. Algorithm will cover up. So just for simplicity, I'm saying all zeros. Even if you put first row as 0, that's also good enough. So let us go to the loop. So I want to show you how you can actually write the loop for this problem. Otherwise, we had already explained what is the procedure. I want to show you how exactly are you going to loop through. That is why I'm writing this. So what should be your loop here? For, let us say, I is equal to 1 to n. Why am I doing 1 to n? Because it is all zeros, so automatically your first row is anyway having all values as 0. I don't have to touch it again with the algorithm. First row is already having zeros. I can start filling from the second row. Okay. So when I'm starting filling from the second row, what should be the inner loop? Let us say for j is equal to 0 to w. What is w? W is the total capacity of knapsack. So this is how my array will look like. This array will have columns equal to w. Total w columns will be there. Rows will be equal to n. Whatever be the number of items, that will be the total number of rows. So not exactly n, it will be n plus 1. Why is it n plus 1? Because first row corresponds to no items. Similarly, first column corresponds to weight 0. So what will happen in this loop? Inside this loop, you have to consider two conditions. One is if you are including it, other is if you are not including it. So inside this, if, what is the first case? First case is if the weight of this item is greater than remaining capacity. So what is the weight of this item? You have a weight array that is provided. From this, you have to pick the weight of this item. So if w of I minus 1, why am I writing I minus 1? Because it is 0 indexed. The array will have first index 0. So the first item will be at index 0. Second item will be at index 1 and so on. That is why I am writing I minus 1 for the ith item. If wi minus 1 is greater than j, the weight of the I minus 1th item, if that is greater than j, what is j? J is the capacity of knapsack at this point. At this point, whichever be the entry you are filling, for this entry, what is the capacity of matrix we are considering? That is j. If the weight of this item is greater than j, what did we learn? We learned we can't include this, because of which what do we have to do? We have to consider whatever happens when all I minus 1 items are there with a capacity of j. So in this case, your entry dp of ij, I am writing the same thing that we just learned. dp of ij equal to dp of I minus 1 j. So the capacity will remain j itself because you are not including this item and the remaining I minus 1 items are available to be included. So what is the next condition? The next condition is, what if the weight is less than or equal to j? Else, so actually I just want to write else, but so that you see what exactly is the condition, I am writing else if. Okay, it only requires an else, but I want you to see what is the exact condition. If weight of the ith item wi minus 1 is less than or equal to j, if this is the case, in this case what should you do? You have to find maximum of what are the two things? First thing is, if you are not including, then dp of ij is the same thing. That is, here you have to write dp of ij is equal to maximum of two things. What are the two things? First thing is dp I minus 1j. This is if you are not including the ith element, then you should include I minus 1 elements. That is, considering the I minus I elements. You may or may not include them, but I minus 1 elements are available for selection. That is what this means. dp I minus 1j. And what is the second entry? From the recurrence relation, what is the second entry? Value of the ith item plus whatever you get from the I minus 1 items, that is n minus 1 here correspond to I minus 1 there, with the I minus 1 items with a weight of w minus wi. So how can you write it here? When you write it here, it becomes value of the ith item, that is v of, how can you write it? It should be like v of ith item is I minus 1. So I minus 1. This is because the same reason. Array is 0 indexed. So in the value array, ith item will be vi minus 1. So vi minus 1 plus dp of, from this array, which should you pick? You should pick dp of I minus 1. And what should be the remaining weight? Remaining weight is J is the weight from which how much is taken away? Whatever is the weight of this particular item. What is the weight of this item? It is W of I minus 1, that is ith item's weight. So this is what you have. This is your complete solution here, and after this what can you do? Once you complete, you can simply return. This is in alignment with this, okay? So here you can do return of what is the item to be returned? dp of last item in the matrix, that whatever be your matrix, in this matrix this last element, that is dp of nw. This will say what is the total profit considering all the n items for selection, and if the total capacity of knapsack is w. So this is what you have to find out. Let us just see this algorithm and understand clearly. We'll just have a walkover. That is knapsack of W, V and W. That is first W, this is the array. Next one V is the value array. Third one is the value of the knapsack, the capacity of knapsack. Then N is equal to length of W, which means N is the total number of elements that are available for selection. Then DP is the matrix you are going to store. In this DP, what does each element mean? dpij would mean it is the maximum value that can be obtained using the first I items. That is, you have the first I items for selection. You may or may not use it, but first I items are available to be inserted, and J is the capacity of knapsack at that point. That is what dpij would tell you. Then you are looping through. How are you filling? Initially all the values are zeros. All need not be zeros. If you simply initialize the first row as 0, that is good enough. Then from the second row you are going to loop I equal to 1 to n. What are you going to loop through? For j equal to 0 to w, that is through all the columns. You are going to fill all the columns one by one for each row. So in each entry, what are you going to do? For that dpij, you want to fill dpij. This is the aim. For filling that, there are two conditions. One is, if the weight of ith item is more than j, that is the more than the capacity of knapsack, then you can include only I minus 1 items, because ith item is anyway useless. It is having more weight than the total capacity of knapsack allowed at this point. So you will include I minus 1 items, and your complete capacity j will be available for the I minus 1 items. That is what this means. So in this case, your dpij will be same as dp I minus 1j. What is the other case? The other case is, if the weight of the ith item is less than or equal to j, that means the weight of the ith item is less than or equal to the capacity of knapsack, you have an option to include this item. Then what should you do? You should see whether including this item gives you more profit or not including this item gives you more profit. How will you see this? You will see the maximum of these two values, that is maximum of not including and including. If not including, how do you write it? You write it as dp I minus 1j. That is, with the I minus 1 items, that is not including ith item, and with a capacity of j, what is the maximum profit? Otherwise, if you are including, then what is the case? If you are including value of this ith item, that is already added into total profit, and with the remaining I minus 1 items and remaining capacity of j minus weight of ith item. This is what is the case when you have the ith item included. You have to find maximum among ith item not included and ith item included. Whatever be that value, the maximum among these two values, that will be inserted into dpij. Like this, you will keep filling each of the items. What is the order of filling here? If this is your matrix, then what is the order of filling here? First row is already fixed because it is all zeros. Then you will fill this block, then this block, this block, this block, and so on. You will follow this order. Final block that gets filled is this one. This is the value which is having dpnw. That is, if you are having all the n items for selection and total available capacity of knapsack is W, then what is the maximum profit possible? That is our final answer. So whatever is the value in dp nw, that will be your final answer. One more thing, last discussion in this lecture is about the time and space complexities. What about the time and space complexities of this algorithm? If you see this algorithm, what are we doing? We are filling all the elements of the matrix. If you have a matrix, you are filling each of the item one by one. So if you are filling like this, what will be the time complexity? Time complexity will be order of n into w. Why is it? Because total number of elements in the matrix is n into w. You have n rows and w columns. So totally n into w elements will be there. For filling each of the entry, you will be taking only order of one time. So total time complexity will be order of n into w. What about the space complexity? You are having this complete table stored additionally, which will cause a total space complexity of order of nw. So both time complexity and space complexity are order of nw. One thing to keep in mind here is, initially when you didn't apply dynamic programming, your total time complexity was order of 2 power n. 2 power n we said is exponential time complexity, and we said we'll be bringing this time complexity down. Then the question is order of nw lesser than order of 2 power n? So here the answer is nw is not necessarily lesser than 2 power n, because this is an NP-hard problem. What is an NP-hard problem? NP-hard problem means there is no known polynomial time algorithm to solve it optimally. So if you want to solve 0-1 knapsack problem optimally, as of now, there is no known algorithm which can solve it in polynomial time. That is why it is called as NP-hard problem. So what you can do is, you can bring up a pseudo polynomial algorithm. Why am I calling this pseudo polynomial? Because of the term w here. See, in terms of n, it is polynomial. But because of w, you don't know what is the value of w. What if w is 2 power n? Then it will be order of 2 power n. So depending on w, it will change. That is why it is called as pseudo polynomial algorithm. But generally, this order of nw is much lower than order of 2 power n, because it is generally considered that your weight will be much lesser than 2 power n. It won't be even comparable to that. It will be much lesser. So if weight is comparable to n, then it is a polynomial time algorithm. So the time complexity is order of nw. In the next lecture, we'll see how exactly each entry is filled. That is, in the matrix, we'll take an example with certain values, certain elements and all. Then we'll see how each entry in the matrix is filled and how you're finally finding the actual profit. So we'll see this in a practical scenario. We'll illustrate the whole process. After the next lecture, the whole thing will be crystal clear for you. So in the next lecture, we'll see exactly how each entry of the matrix is filled. We'll also see how the space complexity can be decreased. There is an option using which you can decrease the space complexity as well. So let us see those details in next lecture.